started. Good. Yeah, so most of us when we hear the word fluids, I think what runs through our mind is liquids, right? Um, but in physics and in the sciences generally, fluids also include gases, right? It includes gases as well. So when you speak of fluids in the context of physics and even the wider, if you talk in sciences generally, right? Fluids refer to both liquids and gases, right? And I mean, there's so much science that has to do with fluids that, well, you can only, we're just going to, what I said, not even scratch the surface, Well, I'm just going to introduce to you some properties of fluids and, how they behave and so on. And one of the things we'll talk about is how they behave under pressure, right? And that sort of thing, right? Um, One of the first properties of fluids, and this is not a property of fluids alone. Even solids have this property, is that property of density. I must mention density, even though it's not clear in your course outline, right? Um, this property is very important because it will tell you so much about the behavior of of um, a certain element and the interaction between elements as well is going to depend a lot on density. You know what I'm going to talk about in just a moment, right? So what's density really? What density all about? Well, the definition really of density in your notes that I sent you, you'll see a little definition, right? It's, and if I were to put it in a layman's term, the density of um, a particular element or an object or a substance really has to do with how closely packed the particles are in that substance, or object, if it's an object, right? Because as I said, density is not just a property of liquids and gases, right? You can have a solid, right? A solid having a certain density, right? And layman's term, I'm using layman's term here. When you speak of density, you're talking about how densely packed. It's a measure of how closely packed the particles are, the molecules inside there, right? How closely they're packed. And the more closely they're packed, you will find that the object is going to be denser, right? The less closely they're packed, the object or the substance is going to be less dense, right? And there's a little mathematical formula to it, really, right? And they'll say that density, and this is a symbol. It's not a P, it's a symbol rho. It's a Greek letter, right? Rho. It's equal to the mass over the volume, right? So this is a measure, okay. If for a particular volume, the object packs or there's more mass for a particular volume, well, then that object is denser. And remember, we said that mass really is a measure of how much material makes up a substance. Remember, we said that? Mass is really a measure of how much material makes up a substance, right? So the more mass you have for a particular volume, the more dense or the denser will be the substance, right? So that's why we say it's really a measure of how much. Notice, like if you have R, let me put, this is a fixed volume, right? And maybe you have some kind of liquid in here, some kind of liquid, right? So let's say this is a 1 liter container. And if there's a particular substance in here, and that substance weighs 1 kg, But then there's another one. Maybe you have another 1 liter container, right? Exact size, right? Exact volume then, right? 1 liter. But this substance inside here is 2 kilograms. Let me write R. This I write outside. If this substance is 1 kilogram and then this substance is 1 kilogram, same volume, which one is denser? Which one is denser? Anybody?
Repeat.
You have a 1 liter container, right? You have a 1 liter container, right? Sorry, I should say you have 2 1 liter containers. You put in one substance in here, some fluid, right? You throw in something here. And it weighs 1 kilogram. Then the other 1 liter container, you throw in another substance in here, another fluid. But now it has 2 kilogram in mass then, right? Which one is denser?
2 kg.
2 kilograms.
Exactly, yes,
2 kg.
yes, because more mass in the same space, right? That's what the formula is saying. It's good to understand what the formula is saying. If you don't understand that, you don't really understand density, right?
So the formula is pressure equal mass over volume.
No, it's not pressure. I just said it.
What?
No, not pressure. This is rho. Rho. It's a Greek letter. It's like a P lean forward. You know when Michael Jackson do that thing where he's lean forward? Yeah, it's like a P, but it's lean forward. It's rho. Right? Yeah. So density is equals to mass over volume. So the more mass that can fit into a particular volume, well, then that thing is denser. Right? And the unit can either be grams per cm cube or kilograms per meter cube. These are the 2 units you will see the density of substances being expressed in. Grams per cm cube or kilogram per meter cube. Right? And I think the notes did give you a whole list of some solids as well as some liquids, their densities. If you look into the notes, it's not a complete list of every substance out there, right? It just gave you a couple of them, right? It gave you a couple of them, right? And you notice like, did you notice gold? Gold has a density of 19,300 kilogram per meter cube, right? If I were to express this as, I think this will be what, 19.3 grams per cm cube. It means then that if you have just 1 cm cube of gold, it's going to weigh 19.3 grams, right? It's going to be it's a very dense element then. Gold is a very dense element. And that is why they use, you see that property is very important, right? Do you anybody know about anything about gold mining? Any gold miners here? Any gold miners here?
Not minor, but I know a little bit about gold.
Okay, and you know how this property is being used in gold mining? Huh? The fact that gold is relatively much denser than many other, like we say sand or or clay, they make use of that property, you know, right? In that what they do, you know, they say wash, all right. Well, gold has gotten so scarce now that basically they wash away the hills and so, right? They wash the soil and they run it over, let me
Sluice
see if I
box.
can.
Some mat. They put mat in the sluice
Yes,
box and pass
yes,
the gravel.
sluice box. You're saying the
Pass
right
the,
thing.
pass the gravel through the box, and the mat is
Yes.
getting the heavier material, which is
So
the
you get
gold.
a little bit of, you know, little thing to chuck up the gold, like, you know, chuck up the thing like, or they have a mat in here. So as the thing falling, the water running over here, because gold is so dense, 19.3 grams per cm cube, as compared to, let me see if they have, they don't have any of the, I don't see, let me see if I can quickly Google the density of maybe sand. Give me 1 second. I'll Google clay, average density of clay. Let me see what they see, if they give me a number. Yeah, all right, this is what they give me here. Approximate density of clay is around, they have here 23, 50 kilogram per meter cube, which is approximately 2.3 grams per cm cube, right? So notice how much more gold is denser than clay, right? You all see that? 19.3 and this is 2.3, right? And something that that you should pick up from the conversation here is that a denser object tend to sink in water because it's heavier. It's just heavier, right? It's just heavier. So the clay is 2.3 and the gold is 19.3. So the 19.3, the denser object is going to sink faster than the lighter object. That is, people use that simple knowledge, and that's how they extract a lot of the gold. Right? I mean, there are plenty of techniques by which they extract gold, but this is just one. And they make use of the density of gold. It's so heavy. For a small mass, it's heavy. So all the little nuggets and so, right away they go down to the bottom, right? They even make use of this idea. I wonder why we talking about gold, right? Yeah. Like when the water goes around a torrent, it tends to slow down a little, you know, because it, you know, it has to overcome this curve here. So when it goes down here, it tends to slow down. And what happens when water slow down? If there's gold dust or gold nuggets and so inside, it will normally kind of go down to the bottom here, right? And the silt is going to continue moving and leave the gold here. That's why guys who would search a gold and so would actually look around a bend and so, you know, when there is a place where the water slows down a bit and gold tend to deposit there, right? Yeah. Anyway, I know I went off there. You know why I talked about it. Imagine, right? We live in this country where so much gold is, and you'd find that our children, right? And our children, our people don't know much about gold. They don't know about how to mine gold. You know, we bring in people from China, we bring in people from Canada, and the people carry away the gold by the plane load, right? And we here, we don't even know how we get in gold, right? We don't even know how we get in. Like, I'm gonna tell you why I talk this story. I was doing a calculus course and I was telling some children how sugar crystals form. And you wouldn't believe me, these are university students, science students at that. And nobody knew nobody knew how exactly the crystals are formed. I say, y'all notice, I asked them a question. Y'all notice how all the sugar crystal get equal size? And I say, how that happens? Nobody knows. So here it is, we have a generation of people coming up, right? And I wouldn't say just this generation, most university students, and they don't know how sugar is really extracted from the cane, they don't know. And it's the reason why Gaisuku has to fail, because, we are not really educating our people. You understand? You ask them, you are interested in bringing back Gaisuku? Oh, no. No, we're not interested. So these are university students don't even know how the sugar is formed from the juice as you boil it. They didn't know. I had to, and I tell them now. One child, she got me a little vexed. She said, "Sir, all right, calculus means small increment, and let me go on now." I said, that is the attitude of, imagine, for 12 years you went to some high school and whatnot, primary school, high school, and you didn't know this thing. And I'm taking my time to explain it, and you were impatient. Right? And she felt bad. I said, I cannot believe that, this is knowledge that you didn't know all your life. People were shocked. Students argued with me and said, "Sir, that is not what the textbook said." I said, the people who write the textbook never went to the factory and make sugar. They're writing any stupidness they want to write. Right? And let me tell you the specific detail that is missing from the text. If you were to boil sugar, anybody knows how anybody works in Gaisuku here? Anybody works in Gaisuku?
So I think most persons, by the time they start work, those places started to close down.
Oh, okay. Yeah, and I think they're trying to close the few factories that are left. It's not something I'd like to see totally happen, but yeah. Yeah, and I was telling the students, they think, they said the textbook tell them, you boil the juice and then crystals will form. That person never went to the factory. If you allow the crystals to form randomly, right, by boiling the juice, what would happen? You'll have all sizes of granules being formed. The crystals will not be uniform. So what you have to do something called seeding the pan. Seeding the pan. So they'll take sugar, grains of sugar, they'll take a pound of sugar, and they'll grind it up. They'll grind it up into fine powder, right? And they'll mix it in ethanol. So they'll take this sugar crystal, the big crystals that you buy from the shop. They'll take it, they'll crush it up fine. And they'll put it inside ethanol. And they'll take it now and give this sugar boil, and the sugar boiler will pour it into the juice. The syrup that is boiling, the sugar boiler will throw it in. And what happens now is that those little granules that are in that ethanol is going to be what we call, it's like the nucleus around which the juice is going to form the crystal that you get now as sugar, right? It forms a nucleus for crystallization, right? Very much like, okay, you all know we say about rain. Raindrops can't fall, can't be made unless there's a tiny speck of dust in each raindrop. They have to have something called a condensation nuclei to grow that droplet around. People don't know that you gotta get a dust in the air. Yeah, it's also true of this crystallization process in the boiler. So they put in this powdered sugar, and each of those fine powdered sugar now grows. And because they're all of the same size, they grow equally. And that's why when you watch the sugar crystals in your bottle at home there, all of them get one size. Now those are what we call trade secrets. So the people who write the textbook ain't got a clue. They never go to the factory and see that happen. You understand? Those are trade secrets that Gaisuku has. But I work there, so I know what they do. That is not in the textbook. So I told the child, I said, just imagine you scoffing at knowledge. I'm teaching you something that you never heard in all your school years, and you read all the textbook for waste time. Right? Don't dismiss it. That's deep knowledge. Yeah, okay. Back to our density situation, right? Good. So we said that okay, density is equals to mass over volume. The units are either grams per cm cube or kilogram per meter cube, right? There's a related quantity. There's a related quantity called relative density. Relative density. I think our textbook, the textbook I sent to you, the notes I sent to you, they use something called specific gravity. They use this term instead of relative density. They're the same thing. And what these two quantity or this quantity is saying, right? What they're doing? They use water because the density of water, and oh, by the way, I should have told you this, that density sometimes depend on temperature, right? The density, especially of fluids, would change according to temperature. So you just don't say the density of like the list I sent to you. I know you see something like, all right, the density of mercury, they said 13,600, right? Don't hold on to that because the temperature, because you know that as what's this formula good? What is formula good? Mass over volume. When you heat fluids, they expand. That's a quality. That's a quality of fluids in that. I should say a property, not a quality, a property. It's a property of fluids. So the volume increases. So if the volume increases, well, then this formula, the value will change. Because the mass remains the same, but the volume increases. That should tell you then that the density will get a little less, not so? Because if you know fractions, if the denominator gets larger, the fraction gets smaller. Isn't that so? So don't hold on to those numbers there because those numbers actually they depend on temperature. Oh, I do see it now. If you watch the bottom of that table that I sent you, you will see there's like a little, is it an asterisk? I can't see very clearly. I think so. And it
No,
says
sir,
it.
it's a small a.
Oh, it's a small a. All right. Young eyes, eh? You see how you got good eyes? You better care it, right? Yeah, I can't say I thought it was an asterisk. It says unless otherwise noted, densities are given at 0 degrees centigrade and 1 atmosphere pressure. So yes, and I think I should extend the discussion and say that densities depend on both temperature and pressure, right? The pressure of the atmosphere, the air around us, right? So when if you were to warm up something, warm up a fluid, it increases in volume and therefore it makes it, the density gets less, right? Because of this formula here. Watch the formula. Like, okay, let me go with something. All right. You got this fluid inside here, right? And it's 1 kilogram. We can't change that. Can't change it. Because the amount of substance there is 1 kilogram. So let's say the container up to here is 1 liter. But when you warm it up, the density might come up. The volume might increase a little, right? Up to there. So the volume is no longer 1 liter. It might very well become 1.1 liter. You know? So if you were to divide now, the density, what happens is 1 kilogram over 1.1 is actually less than 1 kilogram over 1. Oh, well, I think I should. All right. the volume can be in liters, right? It has to be in meter cube or cm cube, right? So let me y'all get what I'm saying, right? Y'all get what I'm saying. That if the volume increases, the density is going to decrease, right? So yes, densities do depend on temperature. It depends on the atmospheric pressure, right? Those are other things. We're not going to get into deeply, these things. But going back to this related quantity here, right? Relative density or specific gravity. They find it convenient, scientists and physicists in particular, find it convenient to compare most substances against water, right? And water has a rough density of 1 gram per cm cube, a rough density. I think it's 4 degrees Celsius. I'll talk about this temperature just now. It's very, very important. Water has a rough density of 1 gram per cm cube at 4 degrees centigrade, right? And because of that now, you can actually compare anything now, or like gold. Gold has a density of 19.3 grams per cm cube. So the relative density of gold to water is 19.3, right? And relative density is really the density of the substance divided by the density of water. So if you were to measure something in grams per cm cube, that's not only the density of the substance, it's also the relative density of the substance. It has no unit. In the notes has some points about that, right? And usually, if something is denser than water, it tends to sink in water, right? It tends to sink in water. It wouldn't flow. And that's why I consider this topic of density, because substances that are denser than water will sink in water, right? Even if you have a substance
Sure.
that is a fluid itself, right? Like oil. You take vegetable oil. What floats on what? Oil floats on water, right? Oil don't. It's funny, right? I don't see. Let me see if I can get an average density. Why are all these ads popping up on my thing here? Density of crude oil. Let me use crude oil. Give me a second. I'm just Googling it, of crude oil. Okay, so strangely enough, crude oil is slightly less dense than water. It ranges from 0.8 to 1 grams per cm cube. That's what at least the internet is saying. So crude oil is actually slightly less dense than water. So it floats in water. Yeah, it only looks so black and you might think it's heavy. It's actually slightly lighter than water, right? It's less dense, and therefore that's why it floats on water, right? Before I go away from water and this matter of density of water, I just want to tell you something that is, I always admire. It really puts me to think. This property of water, right? Water has its highest density at around 4 degrees. At around 4 degrees. You see this 1 here? It's not exactly 1, it's 1 point something, right? You can Google that and see. But when the temperature is 4 degrees, water has its highest density. Now, why is that important? Why is that something that is significant? Well, think of, well, our country, we're okay, right? We're okay. But if you think of those colder countries, so you have a lake, you have a lake. And the lake, okay, it's winter now. What happens to the lake? What happens to the lake? What you see in the movies and the documentaries and so. What happens to the lake when winter comes? Anybody knows?
It freezes over.
Freezes over.
All right. When you say the word freezes over, what do you mean?
More
Sorry,
than
it's
likely, the top layer
encased
turns to ice.
Ice farm.
Where does the ice form? That's interesting.
The top,
It
sir, the
usually
top,
forms
the
at
water
the top.
the
still.
top level, the more higher level.
And y'all know why that happens?
Because the temperature drops.
The temperature more high at the top, probably.
Yeah, it's good to know these things, It's very important. All right. Let me tell you a story that it's you wouldn't believe it. Right? You wouldn't believe it. What happens is that, all right, let me just show you something. I want to just copy this image. 1 second. Let me see if I can copy this image quick.
So the cool air is drop and the hot air is rise.
Come in just now. Come in just. Wait. Yeah. I'll show you something. Right? Now, if you watch here, I'm feeling a little dizzy. I wonder if my sugar level is low. Yeah. This is water here, and this is ice. You notice that water molecules are closely packed. There ain't got much space between here for you to fit anything. But you notice ice? You saw it's open? Plenty space here, because remember another molecule will go there, right? Plenty space. And for that reason, ice is less dense than water, because the water molecules are packed more closely. They're fitting and they left too much space between here. There is space, but not as much space as the ice, right? The ice molecule. See that? See that? These are molecules of ice. Well, this is not one molecule, it's several molecules. This is a molecule, that's a molecule, but the way they're locked together in ice leaves too much space in between. And for that reason, ice is actually less dense than water. Remember, he said density got to do with how closely the particles are packed. So look here. The water molecules are more closely packed, but the ice, they're more spaced out. So there's, it's less dense, and that's why ice floats on water. If that weren't true, oh, by the way, ice might be 0 degrees, lower temperature, and this water here might be 4 degrees. Now, what's significant about this? Water is different from all other fluids. Other fluids, as you heat them, they get less dense. Water, on the other hand, from 0 to 4 degrees, actually, right, it gets more dense. It breaks the rules then. It's different from everybody else. Right? So ice is at 0 degrees. It's less dense than water at 4 degrees.
Sure.
Uh-huh.
Wouldn't that be because like water is like pure and other things, like for instance the aisle, they might contain other substance was actually used to give it a density. So that could be why.
Forget the ones that are even alcohol and so doesn't exhibit this property of water. Are you a religious person, sir? Anybody religious in this class? Anybody? Nobody religious in the class? Sometimes I look at this and I say that water was specially designed, right? This strange property, this essential element that we need to, well, to have the earth, right? To have life, to have everything. It is the only element that has this property. All the other elements, well, they're doing their own thing, right? You heat them up, they get less dense. Water, on the other hand, when you heat it up from 0 to 4 degrees, the one at 4 degrees is actually heavier than the 0-degree one. It's one of the strangest phenomenon on this whole earth. And it makes earth possible. It makes you and I possible. It makes all life possible. Without this, that can't happen. And what happens, going back to our lake story, as water warms up, as the water freezes, you know, so you got water, good. And when the place get cold now, the ice, the water at the top here freezes. And when it freezes, guess what? It forms a barrier now, right? And it traps this warmth here. And the water under here, which is around 4 degrees, right? It actually remains as a liquid then, right? It remains as a liquid, and fish and so can live under here. And that's why them boys just go and bust a hole they break a hole in the ice, put on a hook or put on a bait and catch fish under there, big fish. Without that property, if the whole lake freeze up, all the fish in the world would have dead during winter. But it doesn't happen like that, right? It's one of the things that put you thinking, did this happen by chance? You know, or was this purposely done so that life can be possible? There's so many properties of water, I can't talk about it today, that when you think of its properties, no way, if water didn't have those properties, this earth wouldn't be here and life can't be on the earth. But this special, this one in particular is so special. There are so many more, right? We're not getting into all of them, just because it's related to density, I'm highlighting it. But it's truly an amazing quality or property. I keep using the word quality. We're not using that word so much in the physics. That's more for the arts. Yeah, it's a special property of water, right? Yeah, and usually a lot of times we compare every other substance with water in terms of density, right? In terms of density. Good. So I think I strayed off a little bit there. And we talk about density a lot, right? And how to calculate it. And as I mentioned, when it comes to water and denser substances in water tend to sink in water, right? And you will see a little bit more. We'll get into something called flotation and so a little later. But I want to go to the matter of pressure. What is pressure now? Pressure. And when we talk about pressure, we're going to talk about pressure in fluids in particular, right? We're not going to talk about pressure in nothing else but fluids. That's liquid and gases, all right? And pressure, we can't use the symbol P. You can use a capital P, different from rho, right? And pressure is really defined as, or the pressure of a fluid is actually the force that the fluid is exerting on let's say the container that it's inside. over the surface area that it takes up, right? So if you were to, let me just give you the unit, right? If the unit is either the Newton per meter square or something called the Pascal, right? 1 Newton per meter square equal to 1 Pascal, right? So if you were to have a fluid, right, and let's say, all right, let's have a container, and the fluid up here, it has a weight, a mass of, let's say, all right, let me go with 2 kilograms, right? And the area of the base of this, the area of the base of this thing, let's say it's 1 meter square, right? So the weight of this 2 kilogram fluid is actually what? 2 times G, right? 2G, newtons. So 2G, remember you said, all right, let G be 10, right? So 2G newtons will be 20 newtons. So the pressure exerted by this fluid that is 2 kilogram in weight, if the area that it's actually occupying at the bottom there is 1 meter square, the pressure of that liquid or the pressure due to that fluid in there is going to be 20 newtons over 1 meter square, which is 20 Newton per meter square, or 20 Pascal. Think you get what I'm saying?
Yes, sir. But one more
Yes.
time.
Yeah. You lost him?
So you get the 20.
Sir said, please go it over one more time now.
The thing is 2 kilograms. That's a mass. But the formula says you're actually looking at a force, right? And the force that is acting on the base of this container is the weight. The weight, right? The weight is acting down here. The weight, right? So the weight is 2G. Remember that? Weight is equals to mass multiplied by G, where G is acceleration due to gravity. Remember that? So while the mass is 2 kilograms, the weight, because weight is a force, right? You all know weight is a force, right? So this fluid here, the weight that it's exerting on the base of this container is actually 2 multiplied by G. And we said, well, we're going to use G as 10 in this particular situation, right? So 2G is 20 Newton. So the weight of that fluid is 20 Newton. So the pressure it's exerting on the base of that container is going to be 20 newtons over 1 meter square. As we said, the base is 1 meter square. Not all the time it will be that. I just use nice numbers to illustrate when we talk about pressure of a fluid, what we mean. Think you get it now?
Yes, sir.
Now, something I want to tell you now that I mentioned is the pressure of this, that this fluid is exerting, right? So let me just show you this here. So we had this liquid just now. It's in this container, you know, and we calculated the pressure that it's exerting, you know, or the force that it's exerting on this area here, which we are calling the pressure now, right? P. Now, if you were to take a pressure gauge and measure that pressure, and okay, you come up with 20 Pascal, That's not really the pressure on this container bottom, you know. No. Actually, there's something called atmospheric pressure. In that the atmosphere, you know, all this air around us, the air around us is actually, it has weight, you know. Air has weight. You all know that, right? Air has weight. I hear no comment on that statement. When I
No,
was a little boy,
sir.
huh?
Yes,
Oh
sir.
yeah, wait, Carl. Look,
So
look when you
when you go up,
blow air into a balloon, always come down back.
when you go up at heights, the pressure of the air don't change, increase.
All right, let me give you a little experiment. I remember when I was in high school. So my teacher had a little, you know, a little pivot here, right? And she take an empty balloon and she put it here, you know, flabby looking balloon, yeah. And she air up one of the balloon and she put it on here. And guess what? The balance went this way. And she says this is a simple experiment to show that the air in here has weight because it's heavier than this. Simple experiment, right? So air has weight. And when you are really, most times, when we make all our instruments, we're coming now to a little bit of the instruments they have out there. And probably all of you, you have vehicles and so you know there are these pressure gauges, like the thing that you air up your tire with, right? There's a pressure gauge in it. For those medical people in the room, you know they use this little device. We call it a pressure machine, right? Blood pressure machine. What's the word? It's let me see the word back. The word name. Sphygmo. Wait, let me get it back. Sphygmomanometer. Sphygmomanometer. That's the name of it. Don't laugh me, right? It's hard to pronounce. But we just say it's a pressure gauge, right? Or it's a blood pressure gauge. Right? Or a blood pressure monitor. Yeah. So most of the time, when you have an instrument measuring your blood pressure, right? Or sorry, not blood pressure, any pressure. What you're actually measuring is not what we call the absolute pressure, the absolute pressure, right? What the instrument might be measuring is what the pressure is in excess of blood pressure. Of atmospheric pressure. So when, let me say, okay, this fluid that we started off with, we said, man, it's exerting 20 Pascal. But really and truly, it's exerting far more than that on this base here, right? Because the pressure that is exerted on this base is atmospheric pressure, as well as the 20 Pascal that the fluid is exerting on the base of this container. So it's all this pressure up here, right? It's one, I think 1 atmosphere. They call it 1 atmosphere, right? And 1 atmosphere is roughly how much? I think it's what? How many pascals? Let me just get back. It's around, we will drop out the, we'll drop out the 0.013. I'll just use, what is it? 100,000. 3 and 2, 5, yeah, Pascal. That's roughly 1 atmosphere, right? 1 atmosphere. It's roughly 100,000. 1 by 10 to the 5, yes, 5 zeros. The atmosphere, this column of air, remember this air is miles and miles up in the air, right? So all of that air has weight, it's telling on us, right? So the pressure exerted on this container here, it's actually this plus this 20 Pascal that the fluid is exerting. But usually the measuring instrument we are using will only measure the 20 Pascal. The measuring instrument rarely measures the the pressure of the atmosphere around it, right? The same is true of blood pressure, right? Let me talk a little, and maybe the people in the class, the medical people can correct me and so, right? When you do blood pressure, I want to tell you all something, you know, amazing again. And these things sometimes, you know, they really put me to think. All right? When you do blood pressure, when you do the blood pressure, there's something called, let's call it, what is it? Systolic. You hear what systolic and diastolic? Y'all probably heard these words, diastolic. When y'all ever go and test your pressure and the voice, there are these voice machines. I have one in the house there. When you test your pressure, it says systolic 80 and diastolic 120. Anybody knows? Anybody can shed any light on what that is?
Sorry, the systolic supposed to be 120, the diastolic supposed to be 80.
Oh, really? Did I get it wrong?
Yes, sorry. Upside down.
Okay. Oh, wait. I'm happy. You see what's happened, right? The systolic. Let me see. I'm trying to see if there's a. The systolic is the 120, and the diastolic is 80. Good. So the diastolic is 81. No, the systolic. That's the rate at which, or 120, what they call millimeters of mercury. That's the pressure your heart has to exert to push blood around your body, right? And this 80 is when the heart relaxes now, and the arteries now push blood into the heart. It pushes the blood at 80 millimeter. Medical people correct me, you know. So your heart actually would pump at 120 millimeters of mercury. And when it relaxes itself, so you remember you can't pump all the time. It has to have like one stroke, it pumps, then it relaxes. And when the heart relaxes, your arteries push blood into your heart at 80. Right? At 80, and I think they correspond. I think I did the calculation with, I didn't do the calculation. I asked the internet. Give me a second, let me see what they say. Okay, so roughly, this 120 approximate to around, let me use 16,000 Pascal. And this here approximate to around, let me go with 11 Pascal. It's about 11, it is 10.67 they have, right? Y'all can do the calculation. Sorry, 11,000, right? Or should I round it to, yes, roughly around that. So your heart actually pumps blood around your body at 16,000 Pascal. Your heart is a very, very powerful organ in your body, you know. And your arteries pump back the blood now into the heart at 11,000 Pascal. Right? Now, I want to tell you something that you don't know. Right? If you didn't know, now you're going to know. Yeah, so that show. So let me tell you something now. This is not the actual pressure. The actual pressure, you have to add on, what did we say? 100,000 Pascal. This is actual power of your heart. Right? And this is the actual power, how much? 5 zeros? This is the actual power of your arteries, right? The heart got to push. Imagine that. It has to pump. This is what will get the blood. Remember, it has to push the blood around your body, and it has to also keep you upright and inflated. You know, medical people, tell me if I'm wrong, right? And here you might know better than me. A lot of people think it's our skeleton that keeps us standing, you know. A lot of people think that. But why when somebody dead, they fall down flat? If the skeleton was keeping you up, you're supposed to still stand up. You're just dead, but you stand up. But when a person dies, when the heart stops pumping, you fall flat. Skeleton will do nothing for you. Really and truly, it is your blood pressure that keeps us standing. Right? It is our blood pressure that keeps us standing. You agree with me, medical people? Tell me, you know, you can tell me I'm wrong and so no problem. Like how you correct me just now, I'm happy. I would have recorded the thing wrong and all. Yes. Yes, so it's our blood. Just imagine our heart has to produce all this pressure to keep that blood flow and keeping us upright. It has to beat atmospheric pressure because the atmosphere wants to push us to the ground, flatten us on the ground, right? But it has to keep us standing. So the heart has to produce all this pressure, right? All this pressure. The arteries have to put to provide that, or else our blood vessels will collapse and we'll die. You see, the heart is a truly amazing, organ in our body, and that's what keeps us up. And why? And it's a reason why, as we get older, and so we tend to develop all these blood pressure problems, right? And here's where the well-being part of this course is important, right? It's very important. And I'm not commenting on anybody's bodily structure, but when we are top heavy, you know, we get fat then. You know, this is our body, and we get fat around our belly, right? To keep a body that is top heavy upright, it takes more pressure, or the heart has to exert more pressure to keep. It's like a balloon, you know. If you get a balloon, right? You all know, to keep a balloon up, you gotta keep pumping air in there, right? If the pressure is not strong enough in the balloon, it's not gonna keep upright. The balloon will fall down, so right? Similarly, if you are very, I mean, you get a big tummy. I have a big tummy. I can't laugh nobody. But if you are big on top, if you are top heavy, you know, and your thighs are very slim or slender, you tend to have blood pressure problems. Do you notice that? Or it's not true in your case? Is anybody in the class, you have big thighs but a small body on top? You don't travel with pressure, but you have a big top. Maybe your your belly like me, and for some women, you know, they have how do I say it without causing any offense? They might have they're a little more gifted in terms of their boobs, and they tend to be bigger there. Those people tend to travel with higher blood pressure because the heart has to pump and to keep this big body up here upright. The medical people, you all agree with me or you disagree?
But
I'm getting your thoughts. You agree? I ain't hearing nothing. Yeah. Yeah, don't be afraid, man. You tell me, yeah. So that's why they keep telling you, you know, you don't want to put on too much weight in your upper body, right? Nobody don't tell you, man, your calves too big. Anybody ever tell you that? Your calves too big or your thighs too big? No. Usually that is a person who their center of gravity. If they have bigger thighs, you know, if they have bigger thighs, this course doesn't cover that. But if you have bigger thighs, you know, and a small body on top, right? Your center of gravity is going to be lower. and it's easier for your heart to pump blood around the body and keep you upright. But if you are top heavy, right? If you have a lot of mass around your belly and you have a lot of mass, around your chest area, and you probably have big shoulders, and so you tend to be, top heavy. So, okay, a person with big thighs but a small top is like this. But a person with a big top and small bottom is like this. To keep this body upright is very easy. Has a nice broad base. But to keep this upright, it won't fall over, and it's your heart that keeps you up. The heart got to pump blood in there. It's easy to keep this body up, but it's hard to keep that body up. And that's why the encouragement, for me, I can tell you I'm a bad example. I shouldn't, I'm not qualified to tell you that, man, you need to exercise and all that, because I don't exercise at all. And I've put on a lot of weight around my midsection, and so, which is very bad. So this little bit of physics here about your blood pressure and how hard your heart has to work to keep you upright should tell you that bringing down your weight, in that upper body is very important. You don't want to pack on too many pounds around your midsection and in your chest area. If it's muscles, because that would help, but if it's fat, it's not very good for you, right? So keep all of that in mind when it comes to pressure, and especially when it comes to our blood pressure, right? Or blood pressure. I know that's like heavy stuff. Heavy stuff. Good. Now, something about pressure that you need to know is that as you go deeper in a fluid, the pressure increases. So if down here is, the pressure in this fluid is P1 down here, and the pressure down here, pressure down here is P1, and the pressure down here is P2. As you go deeper in a fluid, P2 is greater than P1, right? And the difference in pressure is measured by a formula, right? Delta P, or the difference in pressure, is equals to H rho G. Now, you see why I talk about density? The difference in pressure is calculated by this formula. The height, that's from here to here, multiplied by the density of the fluid, multiplied by G, G being the acceleration due to gravity. Right? And a simple experiment to show that pressure increases with depth, you take a container, right? And you put a hole here, and you put a hole here, and put a hole here, right? Throw in water inside. And you unplug these holes all at once. You pull out the plug, pull out the plug, pull out. What you find? You find that the water at the bottom here will sport out more far. The water here might sport out up to there. And the water here might barely fall right here. Right? So the reason why this water, the bottom here, shoots out so far is because the pressure down here, P2, or let me go with P3, P2, P1. The pressure at P3 is greater than the pressure at P2 is greater than the pressure at P1. That's a simple experiment to show that pressure increases with depth. And a mathematical way to calculate that change of pressure as you go deeper is this formula here. Delta P equal, delta means change, right? H rho G. We said H is the height, change in height, right? Some places would put a delta here too. They might put delta H, they might put delta H, right? Change in height, right? Rho is density of fluid, and G being acceleration due to gravity, right? And again, I don't know if your work any one of you, your work entail that you have to be underwater and so, right? But of course, this can apply both ways, right? Um, if you, I don't know if any one of you travel overseas and maybe went to America and so, anybody in the class? Hmm?
Yes, sir.
Did you have any trouble breathing there or any trouble with bleeding or so through your nose or what?
The only place I ever had trouble breathing was Chile, Santiago.
Oh, you really? I'm happy that you went south and not north. Everybody going north, right? But I heard going that way, Peru, and so I have a friend who went there. She was living there for a while, and she says it's cold there. I said, what? She says a cold desert, place cold. Yeah, Mercedes, you had a thought?
I had the same issue in Chile. My nose was running blood. I couldn't breathe.
Okay, okay. Uh, and y'all know why? Why that happened? And did anybody tell you why, or did you find out why?
I guess it's because of the skyscrapers. I don't know. I guess it's because of the buildings. I assume.
The
Uh,
oxygen is getting at heights.
all right. So we talk about the weight of the air, right? So whether you go north or whether you go south, remember we are at the equator, right? We're at the equator. So when you go north and you go south, right? Most of those places are very high, right? The places are high. They're not, remember we there, what I said, we there below sea level, something like that. Kind of there, how many feet below sea level? There's this thing they used to say, we're so many feet below sea level.
Sir, it's not
So,
Guyana, it's Georgetown. It's the coast mostly.
okay, all right, yes, all right, good. Thank you for that correction. So we are used to this coast where we're very low. So the pressure on us, right? The air, then the column of air in us is a little higher. So what happens now? When you go to these higher areas, like the girl said, the skyscraper, or if you go into the mountains or higher altitude, the air above you that is pressing down on your body is less. But remember, your heart, because you're Guyanese, your heart is pumping at, let's say you're doing the 180. Remember you talk about the 180 mmHg and the 80, no, sorry, not 180, 120, and the 80 mmHg. Your heart is, let's say, it's doing this, right? And it's used to give you that pressure plus the atmospheric pressure, 1 atmosphere. But when you go to these high altitudes, you talk about, one of the girls mentioned the high buildings or the hills or the mountains. Let's say you go in a place where the pressure is not a full 1 atmosphere. It's a little less, right? Maybe it's 0.98 of an atmosphere. Now remember, your heart is pumping, because you're Guyanese, your heart used to producing this amount plus the 1 atmosphere. So you see this 0.02 difference atmosphere? Your heart is pushing the blood so hard that it's going to damage little blood vessels in your nose and your other parts of your body, and that's why you bleed through your nose. Some people bleed through their ears, right? And that's why our athletes don't do so well when they go, like if they have these Olympic games and all of that, and they go to those cold countries, they're making it because we getting problem with breathing, we get problem nosebleed, ears bleed. And so, yeah, because our bodies, or we grow up here then. And the pressure that our heart is pumping at is a little more than them. Right? So yes, it's very important. That's why a lot of our athletes go there and complain and say, man, I ain't getting to breathe. I ain't even breathe the air thin here. Cause we get nice air, We messing it up though with all this construction and so. But we got nice clean air here. Yeah, so it does affect And those who go underwater, who probably work underwater. When you go down under the water, that extra pressure that acts on you now. If you work for long periods underwater, right? And I know the boys when they do the Barbies River here, when they do some work underwater, they have to go down. Not very much, but for those who go down deep, when they come up back, what it does do with them? They tell them first of all, don't come up too fast. Because when you come up too fast and the pressure on your body is released so fast, what happens? Bubbles form in your blood. There's something called bends. It bubbles in your blood and you will die. It can kill you. So if you do happen to come up from deep underwater, what they'll do, they'll put you in a pressurized tank and they let your body, let the pressure ease up little by little by little by little, you know, and release the pressure off of you, right? The opposite happens when you're in space. When you're in space, because there's no air, right? What happens now is that the pressure is so low, your bones get weak. So when you come back to Earth now, you have problems, your bone paining you because you were used to this place where there's no air, right? I mean, they do pressurized cabins and so where they float around and all of that, but it's not like the Earth. The pressure is far less than the Earth. They just put air in there for you to breathe, right? And they experience weightlessness. When they come down here now, trouble. They have health problems, right? Because of pressure difference. But pressure, right? Pressure, changing pressure I mean, we can use it to our advantage, but health-wise, it can also be detrimental to us, right? So blood pressure is a big thing for those of you in your workplace and so, you know, that's a thing you want to watch, right? Lifting weights and so a lot of maybe your job entail handling heavy weights and so, right? That would make your heart have to work harder, right? And you'll want to limit, you want to, you know, I know sometimes, okay, maybe once in a while you have to lift a weight and maybe you get some colleagues and you lift it. But if your job entail handling weights all day, well, you want to consider, you know, talking to your boss and getting your union involved as to, well, how much weight is safe for you to be, you know, handling all day long, every day.
Sure.
Yeah.
But keeping the body active now be better for the heart.
Yes, but I'm not about just keeping it active, right? But overworking it, right? Overworking your heart is very bad, right? You understand? So you got to consider all of that. Let's say, as I told you before, maybe your body is top heavy. Maybe you have a lot of belly fat. You know, your top of your body is heavy. Your heart is already overworking by just having you walk around. Now, if you have to lean over and constantly pick up heavy weights from the ground, then you have to rethink that, you know what, could we have maybe a forklift doing this kind of thing? You know, maybe there's some kind of, you know, like these boys that have to move around warehouses, they have these, what do you call it? Why am I forgetting the words? Not forklift, there's this thing they roll around, man. It's what? Somebody help me. They pack like the drinks on it and they roll it around. So you don't have to bend over and lift an object and fetch it. You know? Pack it on this thing. What was it?
A trolley?
A trolley, all right. You call it a trolley, yeah. Right? You want to ensure that your workplace provide you with these things, right? Before you go in. Huh?
Like a pallet jack or a trolley?
Okay, pallet jack. I never heard about that one. I know what's happening to me this evening? Maybe my sugar is going down. That's why I'm forgetting these things. These forklifts and so they do most of the lifting in the businesses I see right here. Right? I got an Ansamacal bond in front of me here. And nobody lifts nothing there. Right? Yes, Melissa.
This is the third time I hear you mentioning something about sugar. Can you just have some juice or a sweet or something, please?
Yeah. I think I'm ending the class now because I think my blood sugar went down. Yeah, and the fact that I'm forgetting stuff. All right, we'll end here. What I'll do, I'll find out for sure if there's a semester break next week. If there's a semester break, well, we wouldn't have class on Tuesday. Well, definitely we're not having class on Friday because it's Good Friday. You know, a lot of you might want to go to church and so on, right? So if there's a semester break, we wouldn't have class on Tuesday. And I'll probably inform you if the following Tuesday, I think the following Tuesday is the day after Easter. If UG doesn't open by then, till the next Friday, we'll have a class. I'll let you know though. I'll find out and see what's going on. Yeah, Kinesia.
Sir,
Yeah.
so sir, could you say when we'd get the grades for a test that we've done Tuesday?
What is happening? I'm trying to get up everybody who missed the test. Right? There are a couple of people, I think it's more than 5 people, who have troubles with Safe Exam Browser and all of that. So as soon as I get them and they do the test, I'll release the grades to you.
Okay, sir, thank you.
It should happen before next week. Right? All right, we'll stop there, right? I think I've talked enough. We'll stop there.